Central limit theorem. Recall that the population represents all the observations in the data set. Now, this population may or may not be normally distributed. However, if we repeatedly draw large samples from the population, then the means of the samples will be normally distributed. So let's expand on what we just described here. Suppose that we start off with the population, which is right here. So the population includes all the individual observations. And clearly you could see that the population is not normally distributed. This is what normal distribution looks like. And clearly this is not normal distribution. Now here's what the central limit theorem says. It says if you repeatedly draw large samples from that population, and then you find the average for each of these samples. And then what you do is you plot these sample averages. The sample averages themselves will be normally distributed. So even though the individual observations were not normally distributed, the means of the samples was normally distributed. And that's the whole thrust with central limit theorem. Now, what's the catch here? In order for the sample means to be normally distributed, the samples have to be relatively large. Because if you're just drawing like 2 observations in each sample, and then you find the average of 2 observations, that's a very inaccurate sample mean. But when the samples are large enough, then they become more reflective of the population mean. So let's have a look at the metrics associated with both the population and the sample means. So remember, the population includes all individual observations. So if you find the average of all these individuals, it'll give you the population mean, right? And the dispersion of the individual observations is represented right there by standard deviation. However, for the sample means, let's see what the corresponding metrics would be. So if you found the average of all the sample means, it would actually equal to the population mean. And what's the rationale behind that? Well, where did the samples come from, right? So the samples came from individual observations, right? So it's not like the sample is not representative of the underlying population. So again, since the sample came from the same individual observations, then the average of the samples will be the same as the average of all the individual observations. So that's why the means, whether you're looking at the means of the individual observations or you're looking at the means for the sample averages, it'll be the same because both the sample and the individual observation represent the same population. However, because a sample contains a number of observations, their averages, so the sample averages, will be more smoothed. And the larger the sample, the more accurate it will be, and therefore the less dispersed it will be. So when you're measuring the dispersion of sample means, the relevant measure of dispersion is not standard deviation, but it's a metric called standard error of the sample mean. So let's see how this works. So first of all, the notations here. So this does represent the population mean. That's the population standard deviation, reflects the dispersion of individual observations around the population mean. However, when you're looking at the dispersion of sample means, the relevant measure is standard error of the sample mean over there. And what this does is it reflects the dispersion. Now remember, dispersion, if that's throwing you off, substitute it with errors, because that's what dispersion is. It's an error. So it reflects the error associated with sample means. But let me ask you a question. What do you think would happen to the sample errors as the sample size got larger? Well, if the sample becomes larger, then it becomes more reflective of the underlying population, and therefore there'd be less error and less dispersion. So when you're measuring dispersion of a sample mean, we need to take into account the sample size. Specifically, we take the square root of sample size. So that's how we find standard error. We take the standard deviation of the sample, and then we divide it by the square root of the size of that sample. And as I stated before, as the sample size increases, the standard error, in fact the word error is built in, decreases. But ladies and gentlemen, this should be something that we need to understand conceptually. We shouldn't be needing to look at a formula or a framework to reach this conclusion. The bigger the sample size, the more reflective the sample will be of the population, and therefore there'll be less error, and as a result standard error would decrease. And we just elaborate on it. So as sample size gets bigger, accuracy increases, therefore less deviation or less error or less dispersion between the sample mean and the population mean itself. So let's illustrate with an example here. Suppose that our data set contains 60 observations, and the average of that data set, so the data set refers to sample here. So the sample average was 10%, and the standard deviation of that individual observation, so remember we had 60 observations, and maybe we should expand on this just a little bit. You have a group of 60 observations, and you have one number representing the entire data set. So you're saying the average of those 60 observations is 10. Well, what's missing here? Well, how dispersed are these individual observations around the sample mean? And that's what standard deviation is trying to tell us. It says on average, the individual observations in here deviated by 12% from the sample average. Because remember, you're going to have some observations here that are less than 10, some observations greater than 10. Don't you want to know how far away these individual observations are from 10? And that's exactly what standard deviation tells us. Now note, the average deviation of individual observations around the population mean is 12, which I just discussed. However, the average deviation of the sample mean, so do you see how we're looking for a different thing now? In the first case, we're looking for standard deviation of individual observations. So this goes back to our visual framework. See the big difference, right? So this is the individual observations. If you want to measure the dispersion of individual observations, you're looking at standard deviation. But remember that whole speech we did about sample mean and how the bigger the sample size, the less dispersed the sample means will be. So if you're looking at dispersion of sample means, we look at standard error and not standard deviation. So there it is. So if you're looking for a deviation of sample mean, we got to look for standard error. Therefore, we take that standard deviation. So it's the same framework here, ladies and gentlemen. It's just standard deviation divided by the square root of n, so we get 1.55%. So do you see the difference? So if you're looking at dispersion of individual observations, they are dispersed by about 12% from the mean. But if you're looking at dispersion for sample means, they're only dispersed about 1.55%. Why is the dispersion less for these sample means? Well, because sample means contain more observations than an individual. So an individual observation, that's just one observation. In our case, the sample mean contains 60 observations. So of course, if I'm looking at the mean of 60 observations, that's going to be more accurate than if I'm just looking at an individual observation. And if it's more accurate, it's going to result in a lower dispersion, in this case 1.55%. Now tip, later on as we get to confidence intervals and hypothesis testing regarding population means, we always use standard error and not standard deviation. And the reason for that is because if you're doing these tests or confidence intervals for mean, then I need to know what the dispersion is of mean and not individual observations. So do you see the connection? Here it is. Right? So there it is. That you just have to remember that. And why am I sort of dwelling on this a little bit? Because if you do not make the conversion from standard deviation to standard error, in other words, if you simply use standard deviation when we do confidence interval and hypothesis test, you'll get the wrong answer. So it's something we need to be mindful of.